go.
When I asked him if we were going to have a test, he was like, oh, we're not going to have a test after.
Yeah, for Mr.
Zoom, zoom.
I've been, last year.
All right, let's take a look at this thermo quiz review. Is that all we have for today? Thermodynamics review. What was that? Was that something that you could download on Friday?
Yeah.
You may need to go back to Friday. What I'll try to do. Hey, guys. Shh. I'm going to have to kick these non-Zoomers out. I haven't had to kick anybody out yet. I have Jeremy Mormon, though. He has been close. If you know that tennis player kid. All right, so let me see if I can help you out on this. That way you don't have to go back to it, but it's under thermodynamics. And it is the review. Somebody sent me an email last night at 8:30 p.m. Mr. Jackson, when are the answers to the review going to be up? I'm like, what, dude? Trying to watch this show. And so I am working on that currently. I'll take pictures of it and put it up there. I'm going to turn the lights off here so these guys can see. What's it do if you click on that test? What does it do if you guys click on it? It doesn't let you take it, right? Hudson, well, if I ask Hudson to talk, then he's going to freeze on me. Olivia, if you click on that test, what does it do?
1 sec.
It's locked for me.
Okay, cool. That's what I want. It will be available tomorrow morning until 11:59 p.m. Tomorrow night.
How many questions is it?
I believe it's 20.
Will there be like multiple choice and then like calculations as to how it's going to be worked?
The most random one I've ever had. I've got some really cool test things that I'm trying out with this test. Lucky you guys, right? There's like drop downs. I got that stuff in there. I've got a multiple choice, and I've got numerical answer ones. All that stuff.
Okay. Thank you.
Yep, you're welcome. And it kind of gives you some instructions like on some of the numerical answer ones, like do not round, stuff like that. Try to make it better. But I believe it's between 20 and 25 questions at least. It's a harder one to do than just that because like one question may have 3 different parts and stuff. So just keep that in mind. Like a way to test units was to sit there and have a drop-down menu of units. So you could put the numerical answer here and then put the units here. I got kind of carried away with it. Wednesday, we begin, and I'm so glad that this worked out. We begin the quantum mechanics unit. This stuff gets crazy. You know, like I probably know 5% of what, you know, the string theory guys and like Stephen Hawkins knew and some of those guys know. I know about 5% of that, and I'm going to teach you about 5% of what I know. So like you're getting a very small sliver of it. But it gets kind of crazy. So I'm very happy that that it worked out that we get to do Wednesday and then take kind of Thursday off because of the whatchamacallit. What did I do? Because all you guys have to do that stuff. Quantum mechanics, lessons, box diagrams, electron configurations. Yeah, that's fine. That's probably the easy part. The hard part is the first day because you'll be sitting there going, what is this guy talking about? This is insane. And all of a sudden on day 2, you'll watch the video on the box diagrams and electron configurations and you'll be like, oh, that's what he meant. Hopefully at least. Some of you might still be like, what? Boxes now. And then Friday, We'll do noble gas configurations and review quantum mechanics. I plan on doing an in-class Zoom on Friday, but it looks like plans may change for that. So I'm hoping to do it, but it's iffy right now. If not, obviously there will be a video for you, just like earlier in the year. There cannot be a class Zoom on Thursday because I will be talking with my personal project kids because we're still doing personal projects. We're still doing them. Right? Yeah. Lucky you guys. If you don't do them, then you can't get senior parking or whatever. Or whatever the punishment is. So that's it. That's the week. To tell you the truth, this week is kind of easy. And then we get back and we only have 2 weeks before finals, I believe, right? So then we'll finish up quantum mechanics with math. And then we'll bump into what's called periodic table trends. And then probably instead of testing on this unit in the past, what we've done is we've just made the final exam have it be heavier weighted towards this unit. So just keep that in mind. Like out of the 50 questions on the final exam, like 10 of them will be this unit. So it kind of makes this worth 1/20th of the final exam, which then breaks off into, you know, the other units test plus the final question. All right.
Wait, Mr. Jackson?
Yeah.
Wait, so the final exam's only over these 9 weeks, right?
No, final exam's comprehensive.
Oh, okay.
9 weeks test was only over the first 9 weeks.
Oh,
This is the semester exam. Oh, who is that? Is that Akshay?
yeah.
Yeah. You may not have the final. Did I give you the final exam review packet?
I don't know.
If you don't know, then I'm probably going to say I didn't. But I thought I might have. I might have sat there and said, hey, you need to be responsible for all this junk, but I'm not quizzing you over it. Let me show you where you guys can all find the final exam review packet if you've lost it. It's going to be at the 9 weeks. So that was before stoichiometry. September 4th, maybe? Nope. Wait, it couldn't have been this, could it? Okay, let's do it this way. September 4th. Nope. I believe it had just the combined gas law stuff on it. Here we go. 9 weeks test. So we're going to be looking for the 9 weeks, the final exam review packet right here. Wednesday, September 30th. I'll tell you what, why don't I just copy that link and I will put that in this week's. For those of you that are like, I need better grades, then you probably should be looking over that. If you're failing, the cool thing now is that all you've got to do is pass the final and you can pass the class. You guys heard this? Isn't that amazing? I'm going to put it right under here. Actually, I'm just going to go to files. I wonder what that would be under. Exam reviews. 1X Study Guide 2019. That probably sounds like it. Yeah. What's that Drew Carey thing? Like North Central, where the points don't matter and everything's made up. Let's see if that's it. There you go, Akshay.
Okay.
That's the final exam review pack. Look at that. That's the only thing we have left after this week. Whoop. And I've been thinking about taking out quantum numbers. They're not required for the AP exam. I'm not sure why you would ever need to know quantum numbers. Basically, quantum numbers are the solution to three-dimensional calculus. How many of you have done three-dimensional calculus? What's that? No. It's not on the AP test for AP chemistry. All right, without further ado, let's take a look at this review guide. I think that's a pretty good description of how the week's going to go. We are running out of weeks. Hopefully everybody's safe at home and everybody's family is safe. Oh, somebody is putting on the chats. You know I don't read the chats. This is unrelated to the study guide, but I just remembered and I don't want it as a teacher. Are we getting back to the 8 a.m. start time? Yeah, we're getting back to the 8 a.m. start time after Thanksgiving break. The rest of this week, which actually is, well, Tuesday, Wednesday, and Friday, the rest of this week is the 7:20 start time. To tell you the truth, I don't know what Thursday looks like at all because I don't know, because I haven't thought about that far ahead yet, Thursday. But after break, we go back to kind of a weird one, I think. Every day has a homeroom. So basically, it's the Monday schedule. But when I say every day it has a homeroom, I don't mean that we have to watch those stupid creek flowing movies or sit there and then talk about our feelings. We only do that on Monday still. The other time of the homeroom is actually it's a tutor time for you to actually talk with your teacher. So it's like, what do you call it? SRT time or something. Other schools like Carmel calls it something else where they like, it's like basically just a help session. What this is going to do, I think, is it's, instead of teachers having after school hours, is that if you want to get help from them, you meet with them during that time. I mean, maybe 2 people have come into my after school hours over this year, and then they left real quick. They're like, okay, I'm good. I'm just going to look it up. So yeah. So I don't know if this SRT time or whatever, this study teacher resource time or student teacher resource, SRT, STR, student teacher resource time. I don't know. Anyway, whatever it's called, that's going to be every day. So that means we can make up work that you're missing. All right. So let's take a look. If you've not done any of these, I'm basically just in the process of filling this out. I'm going to take pictures like I do of this after I'm done and set it up there. But if you have a question over any of these, I can take it now. If you've not looked at it since Friday, that's fine too. I can do 5 and 6 as a little quick practice with you. And then we can, you can stay on and watch me finish the rest of it, or you can head off. So let's just do 5 and 6 real quick. So here's 5. It says we have some ice at 0.0 degrees Celsius and placed in 244 milliliters of water at 28 degrees Celsius. All the ice is melted and the final temperature of the water is 26. How many grams of ice melted? All right. So some ice was put into 244 milliliters of water. That is the mass of water because water has 1 gram per milliliter. This is the temperature initial of the water. This is the temperature final of both. This is the temperature initial of the ice. Right? So we've got to, 1, get that ice down from ice to, help me out, from ice to water.
Water.
There we go. And how do we do that? Well, we take the mass of the ice, and every 1 gram of ice requires 330 joules to melt. Correct? Plus, we then have to get that ice from 0. And this is kind of funny if you're missing points on your laboratory for this, oh, I may have went back because I felt bad and gave everybody the points because it was silly. But you should go back and check your laboratory. Somebody's like, I didn't know you wrote things on our stuff that we turned in. I hand grade all the stuff that you guys turn in. Like I write notes on there and show you like how many points you get and stuff. You should go back and check the laboratory where you guys took the ice and melted it, because a lot of you were using the specific heat capacity of ice here. This ice just melted. We are now taking that ice and it's no longer ice. So whatever its mass is, we're timesing that by 4.184 joules per grams degrees Celsius. Like if you were like at 78%, like what is it, 78% error, you probably had like the 2 point whatever it is heat capacity of ice. It's melted. We are now changing the temperature of water. So that was a big problem with some of you guys. That is 26 degrees Celsius. That's how much we're changing it. And this all has to be set equal to 244 grams of water at 4.184 joules per grams degrees Celsius. And 2 degrees Celsius. Does that make sense for the setup? This is the ice melting. This is the ice changing temperature from 0 to 26. This is the water going from 28 degrees to 26 degrees. Questions about this? You guys see that okay? You need me to move my picture? All right, so let's do it. You know what? I shouldn't confuse you. I'm going to go ahead and get rid of that M, and I'm going to put their X grams again, because these are the same thing. This is the mass of the ice. This is the mass of the ice, the water that was formerly ice. 244 times 4.184 times 2.
It's 2041.792.
So that's how many joules we have to work with. 4.184 times 26.
The answer is 108.784.
Does everybody see the math that I've done there? I'm sure that the mathematicians or whatever, I'm sure that they have some fancy word for that. So I found the product of the X here and the product of the X here, and now we're going to sum these products. 333 plus 108.784.
It's 441.784.
$2,041.79 divided by 441.784.
It's about 4.6216.
$4.62 grams. Conceptually, does this make sense? Melted the ice. Change the temperature of that same mass of ice from 0 degrees Celsius up to 26. We've got to use because it's now melted, it's no longer ice, we've got to use a specific heat capacity of water. What a lot of you did on that laboratory, what I'm saying is a lot of you guys use the specific heat capacity of ice. What is the specific heat capacity of ice? Is it 2.1?
Yes.
Yes, thank you. All right, let's do a Hexer's law. So I need to change this C2H6. Here it is. So I need to double it and reverse it. Flip that, double it and reverse it. Then I've got the CO2 on this side. So I just got to double this. And that's going to give me 4 H2O. And if I keep this one the same, if I multiply this one by 2, that will give me 6 H2O. Since this will be 6, this would be doubled, this will be 1. So all I got to do is double this as well. So some people can sit there and do that, and then they say, okay, 2 times negative 337.2.
It's negative 674.4.
2 times 32.7.
The answer is 65.4.
We get rid of this because we reversed it too. 2 times negative 68.3.
It's negative 136.6.
And then they just add all these together. Negative 136.6 plus 65.4 plus negative 674.4.
That would be negative 745.6.
So that's the way that some people do it. That's a shortcut. I am going to show you the check way because I think the check way is better. It is not as fast, and you do have to write more stuff, but we are reversing number 2. So 2C2H6 yields 2C2H4 plus H2 plus 2H2. And then I change the sign, and then I do this. Delta H is 65.4. Done. Now I see that I need 4 CO2s on the product side. So this is the only place that CO2 exists. So we need to multiply that through. 2C2H4 plus 6O2 yields 4 CO2 plus 2H plus 4 H2O. And that is negative 674.4. Once I see that, I can see I need 7 O2. So I can take the 1/2 O2 and realize I need to multiply it by 2. Or I can see the 4 H2O and I need 6 H2O. So I need to multiply this 1 H2O by 2. 2H2 plus O2 yields 2 H2O. So we multiplied it by 2. So that is negative 136.6. The cool thing about this part is you can sit there and go, oh, there's my 2 C2H4s. I'll cross those out. Oh, there's my 2 H2s. I'll cross those out. Oh, there's my 6 O2s and 1 O2 for a total of 7 O2. Oh, there's my H2O and my other H2O for a total of 6 H2O. That's what proves that this all works. But if you can do the shortcut method, by all means, do whatever. Do it however you want to do it. This is actually where I get a little bit more nervous for you. It's these little questions where it's a multiple choice and you've got to think. So hopefully this isn't too difficult for you. Give me 1 second. Weird. All right. So 2 metals of equal mass with different heat capacities are subjected to the same amount of heat. So you can do this, M and M. Their masses are equal, right? They're also subjected to the same amount of heat. There's one and there's the other. Which undergoes the smallest change in temperature? Well, if we rearrange this equation to solve for delta T, right? the mass and the Q are the same. So let's just call it then whatever over C. Let's just call it whatever. Let's call it X over C. It's the same amount for both. Which undergoes the smallest change in temperature? Well, whatever X is, let's say X is 100, right? How could we make a smaller delta T here? What does C need to be? Does it need to be a big number or a lower number?
Bigger.
Bigger. The bigger the heat capacity, the harder it is for that temperature to change, right? So the metal with the higher heat capacity would be the one that undergoes the smallest amount of change. You don't need to know the initial temperatures of the metal. You don't need to know which metals you have. They both don't undergo the same change in temperature because it says they have different heat capacities. There's the formula to figure that stuff out, right? It's just like, remember the gas law test? Think about how well you did on the gas law test. I just did question 5. Hopefully you saw that, Ian. Think about the gas law test. Did you do well on the you know, the part where it said, you know, if I double the temperature, what happens to the pressure? You know, those type of questions. There's no numbers involved at all. There are some of those on this one. A 25-gram piece of aluminum is heated to 82.4 degrees Celsius and dropped into a calorie room. That's basically the same type of problems we've been doing. This time we're just trying to solve for the mass of the water instead. So that's going to be a Cm delta T equals Cm delta T. And it's not even a temperature one, so it's not even that hard. You're just going to be solving for the mass of water. I can do that one on my own, unless you want to see it. Let's take a look at the next one. 30 milliliters of pure water at 280 Kelvin is mixed with 50 milliliters of pure water at 330 Kelvin. What is the final temperature of the mixture? Again, Kelvin, Celsius, it doesn't matter because they go by the same increments. So a change in temperature, a change in 1 degree Kelvin is also equal to a change in 1 degree Celsius. So that doesn't matter. Consider the reaction, blah. What are we doing here? Make a water. Here's the delta H, negative 286 kilojoules. Which of the following is true? Is it exothermic? You can barely.
Yes,
Yes. How did you know?
because it's negative. It lost heat.
Good. Is it endothermic?
No.
No. The enthalpy of the products is less than that of the reactants. Is that true?
Yeah.
Yeah, it is. The amount of energy that the reactants had is more than the amount of energy that the products have because it released energy. What are you doing out there? Heat is absorbed by the system?
No.
No. Both A and C are true? Yeah. So there we go. The total volume of hydrogen gas needed to fill the Hindenburg was 2.00 times 10 to the 8th liters at 1 atmosphere and 25 degrees Celsius. How much energy was evolved when it burned? Oh, this would be a good little final exam question, wouldn't it? In order to use this formula, we need to know the moles of hydrogen we have. That way we could use the molar, the molar heat value of the reaction, or the heat of the reaction, right? For every 1 mole of H2 that burns, you get 286 kilojoules given off. How can we get the moles from liters, atmospheres, and temperature? This possible student of the month material here.
Is it the PV equals nRT equation?
It is. It is. Was that you, Ian?
Yeah.
See what the month is. I don't know if anybody else is up on it, but that might be it. The month is something like knowledgeable. Sir, you have got some knowledge. All right, so let's take a look at that then. PV equals nRT. What are we going to solve for?
N.
Yeah, N, right? What I say I wanted. N equals RT over PV. So 273.15 plus 25.
It's 298.15.
That is V.
Wouldn't it be PV over RT?
Yeah, who was that?
Margo?
You got some competition now, Ian. Better watch it. I adjusted the wrong side, didn't I? Good catch, Marva. We want to divide both sides by RT. So PV over in, geez. Not putting a third name down there in one day. RT, there we go. All right. What is this number? Is that 200 million? So, see if I can do this. 200 million divided by 0.0821 divided by 298.15.
The answer is about 8,170,563.7872.
That's what I got. Anybody else get anything different? Check my work on that. I feel comfortable with that. That is moles of H2. Every 1 mole of H2 gives off 286 kilojoules. 8,170,563 times 286.
It's 2,336,781,018.
Boom. 2.4 times 10 to the 9th. I like how she says about. Blah, 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 blah. And that is kilojoules. And some people sit there and say, well, why didn't you put negative 286? Again, I knew it was giving off this energy, right? It says how much energy, and I know that can get confusing to you. I'm not one of those guys that's going to try to trick you with positive and negatives on the test. The problem, though, is the way the test is if you put negatives on some stuff, you may end up getting it wrong. Carefully read what it's saying. How much energy was evolved when it burned? You know, if it says something about is the delta H of the reaction positive or negative, yeah, then sure, you're going to have to sit there and say it's negative. But if I'm talking about energy, I usually ask how much energy is lost. That's still a positive amount. We know it's lost. So, I mean, it wouldn't be a negative amount of energy, though. It would be negative to the system, but we're saying it's lost. So just keep that in mind. When you're doing formulas, though, remember, if something is losing and something is gaining, one of them has to be negative. Otherwise, your final temperature minus initial temperature won't work out right. Something's final temperature minus the initial temperature should be negative because something is losing energy. I only have 3 more problems to do. I'm going to do this one on camera, then I'm going to do this one on camera and this one on camera. You don't have to stick around for it if you don't want to. Then I'm going to take pictures of all these and post them on to today's date.
Wait, Mr. Jackson,
Yeah,
isn't there a third review page, page 4?
there is. It's already done though. I did that over breakfast. You want to see one of the problems done on that?
Kind of confused on number 2.
What? Oh, yeah, number two. Number 2 is like the one that may have gotten Ian student of the month. You have to pull back to stoichiometry. So it says how much heat is released when these two mixtures are put together. Now, yeah, so every 3 moles in the reaction of Cl2 will produce 232 kilojoules. And every 1 mole of CS2 will produce 232 kilojoules. The problem is that first we got to get the moles of each of these substances and then figure out how much each one could produce. Why can we only produce 10.9 kilojoules? Because why?
Because it's a limiting reagent.
Oh, yeah, that's right. It's a limiting reagent. We don't have enough chlorine gas to produce any more than 10.9 kilojoules. So we can't possibly produce 30.5 kilojoules. How exciting is that, bro?
Okay, cool. Thank you.
You're welcome. I'm trying to think. I think number 3 on here has the most whiteout. I'm not sure if that's because I wrote something wrong or if I just had to, if it looked like garbage and I had to rewrite it. Don't do number 5 on here because I don't know what the heck it's asking for. It almost seems like something's missing. I wrote all the equations in words, but I couldn't figure out, like, yeah, it looks like something's missing. I don't know. Don't bother with it. Even though I did something here, that was before I realized that there is no real problem. It has an answer, but I have no clue. It may be something like it gives you an equation and it has you rearrange these using, what's his butt's law? Hess's law. What's his butt? Oh, this one was cool. This problem right here is pretty cool. Basically, keep in mind that 1,000 liters of water is 1 kilogram, which is 1,000 grams. And then you're basically dropping this potassium off in it. So you got to convert the potassium into moles. And then you use how many moles you got to figure out the energy. And then once you've got the energy, you've got this 1,000 liters of water that you're giving that energy to. So then you got to figure out how much it raises its temperature. Definitely a fun one there. All right, that's all I got. If all you want is answers, then you are more than welcome to leave. If you want to watch me do some more stupid pet tricks, if you want to watch me do some more of these, you're more than welcome to hang out and watch them. Have a great day either way. What time is this class over? Tomorrow, you don't have to Zoom with me. You can just take the test, but we're going to try something fun with the black team. So join us if you want, because they can't take the test. They want to be able to do it at home. All right, so let's take a look here. I've got CLF. Oh, this is tricky looking. This one looks a little bit fun. So if we take a look here, you probably all should have stayed for this one. Hopefully this is not one like this on the test, right? How do I make 2 into 1?
Multiply it by 1/2.
Multiply it by 1/2. So we get CLF plus 1/2 O2 yields 1/2 CL2O plus 1/2 F2O. Oh my God, I'm so brilliant. I put on the recording. That's amazing. I'm so glad I did that. So I was like, this one really should be recorded just in case those guys want to look at it. Man, I'm like, start of the period me, brilliant. All right, let's take a look then here. We've got CLF3. We have CLF3. So what do I need to do to this one right here? 1/2 167.4.
It's 0.5.
No. 167.4 divided by 2.
It's 83.7.
All right, one more time. I've got CLF3 here on my equation, but I have 2 CLF3 here. So again, I need to do what to that? I don't think anybody's paying.
Multiply by 1/2.
1/2 again, good. And since it's on the opposite side, I need to reverse it. I think it's just you and me, Raylan. Everybody else got out. If you want to leave, you're more than welcome to.
I think there's still some people on here. It
Oh,
says there's 6 other participants.
oh, okay. I thought it was just me and you. All right, so then we have CLF3 plus O2. Last but not least, this F2. Well, let me do this. We need to cut this in half and then reverse the sign. 341.4 divided by 2.
It's 170.7.
So again, what do we need to do to this one to get from 2 to 1? I'm not going to make you say it again. You know it. All right. Negative 43.4 divided by 2.
The answer is negative 21.7.
All right, so there we got it. So if we take a look, I'm going to show you why it works. So the F2 stays. The 1/2 O2 and the 1/2 O2 cancel out 1 O2. And the 1.5 F2O, well, there goes one of the F2O. There's the other half. The 1/2 Cl2O is there and there. So we get CLF plus F2 yields CLF3. So all we've got to do now is add these. 83.7 minus 170.7 plus,
It's negative 87.
hey, calm down. 83.7 minus 170.7 minus 21.7.
It's negative 108.7.
There we go. Questions on that? All right, let's take a look here. 30 milliliters of pure water at 280. They didn't really give me a lot of room for this. At 280 K is mixed with 50 milliliters of water pure at 330 K. What is the final temperature of the mixture? So we're going to set these.
Could you put
What's
Sorry,
that?
that's okay. Could you put those equal and solve for T of F? That's what you would do, right?
That's exactly what I'm going to do. So I'm going to do 2 of the different QM delta T's. The cool thing is that, well, the hard thing is that I'm solving for final temperature, right? So that's a little bit weird. The cool thing is I don't have to worry about 4.184 joules per gram degree Celsius because that's going to cancel out, right? So we're going to get 30.0 grams T of F minus 280. 50.0 grams T of F minus 330. 50 times 330.
The answer is 16,500.
Remember, I do have to make this one of these sides negative, don't I? Doesn't matter which one I do it to. Did I say that right? 16,500. 30 times 280.
It's 8,400.
So what I want to do now is 16,500 plus 8,400.
The answer is 24,900.
24,900 equals, and I'm going to take both sides and help me out here. Add 30 to both sides. So that will be 80 T of F. 24,900 divided by 80.
It's 311.25.
There we go on that one. Last one. A 25-gram piece of aluminum, 25 grams of aluminum, has a molar heat capacity of 24.03 joules per grams. Oh, look at that. It's not joules per grams degrees Celsius. It's joules per mole degrees Celsius. What does that mean? I have to do this 25 grams.
Convert it to moles.
Yeah, what a sneaky thing to try to do. 26.98, messed it up. 25 divided by 26.98.
That would be about 0.9266.
That was a dirty trick for whoever teacher made this thing. Very dirty trick. You okay? What happened?
So in my there are random songs that'll come up that are like really loud.
Oh.
I don't know why I put them there.
This is also kind of tricky. It says that it's at 82.4 degrees Celsius and dropped into water initially at 22.3, but the final temperature of the water is 24.9. So what does that also mean for the aluminum?
The final temperature is 24.9.
Oh, is Margot even on here still? 82.4 minus 24.9.
The answer is 57.5.
So we're going to multiply that, and we're going to set that equal to M 4.184, 24.9 minus 22.3.
Wouldn't you do 24.9 minus 82.4?
Ah, thanks. 82.4 minus 24.9.
The answer is 56.
Oh, no, yeah. It's okay. Since I don't have to solve for T of F, I can just set these equal to each other and not even worry about it. And I can look at the change in temperature as just a constant thing. But yeah, if you wanted to do negative and then put a negative sign there, you can. But basically, the only time I really need to worry about that is if I have to solve for T of F. Otherwise, it won't work out correctly. I can make these things like absolute value, and that gets rid of the negative on the negative side. If you want it, I can put it there for you. Negative, negative, but it's just going to go away, isn't it? Yes, yes. Who asked the question?
Yeah.
Yeah, it's just going to go away. So I can definitely put it there for you. Where was I? Is this correct? 2.6. Yep, that looks correct for degrees Celsius. 4.184 times 2.6.
It's 10.8784.
Negative 0.9266 times 24.03 times negative 57.5.
It's about 1,280.3063.
Now it's just a division problem. 1,280.306 divided by 10.8784.
It's about 117.6993.
Why did you use 2.6? Oh, wait, that was the change in temperature.
That's
Just
the
kidding.
change in temperature for the water. How many significant digits will we have on here? 3 probably, based off of the mass of the aluminum. There we go. I think I gave you like 70 minutes for this test. Totally up to you how you want to do it. This class merges with the lunch, so if you want to start at lunch, you're more than welcome to. You want to wait till, you want to have a nice long lunch and then wait until later in the day, that's fine as well. I don't think it should take any longer than 57 minutes in normal classroom. That's what we used to do it when it actually had more questions on it last year when we took it, and students were about the same as always. Most of them were able to finish it. The ones who struggled maybe stayed 5 minutes after class or something like that. But just keep in mind, you have 70 minutes to do it. That's what I've given you. Other than that, I think that's it. Questions? Just because I am done on here, you can ask it and we can try to redo it or something if you want to see one that I've already gotten done. All right, Ian. As I said, you don't have to come to the Zoom tomorrow, but if you want to, we're going to try to do something cool. I'm going to try to set it up for these guys right now, and then I will see you guys tomorrow then. Have a great day.
I do have one question, actually.
Yeah.
So will there be problems on the test that have like PV, NRT, and the limiting reagents on it?
I wish. There won't be.
Okay, good.
Will you do number 6 on page 4, Mr. Jackson?
6 on page what? Last page?
Yeah, the last page, page 4.
Oh, wow. I didn't even realize there was a back to this. I didn't even do any of these yet. You want this one. All right, so the first thing that you want to do is you want to change the grams of potassium to moles. And then using this equation right here, every 2 moles of potassium makes 278.4 kilojoules. And that's what I did right here. So it's 17.8 kilojoules. I then took Cm delta T and set that Cm delta T equal to that kilojoules. But instead of using kilojoules, because the heat capacity of water is in just joules, I changed it to joules. So instead of keeping this in kilojoules, I changed it to joules because the heat capacity of water is in joules. And then I just took the final temperature and minus the initial temperature, which was the 24. And I divided both sides by this. And then I set it equal to this. So then we add 24 to both sides. And we get 28.3. So first you...
Okay, that makes sense.
Yeah. All right.
Thank you.
You're welcome. Is that the end of this class? Yeah, but that's the end of this. You know what? I'm not that smart because what I did is I recorded both of my classes together in the same Zoom. I can split it. I can split it.